Hello everyone, I'm Henry Wildberry, and today I have something a little bit different planned for this video. Yes, we are going to rewind all the way back to my former self when I used to make technical cycling related videos. More recently, I've been doing vlogs and even satirical videos, and I've kind of gone away from doing this. But a few of my longtime subscribers who subscribed back when I was doing this have reached out privately and they've asked for more technical content. So today I'm going to give this a try. We're going to see how this goes, and if all goes well, maybe I'll do some more of these in the future. But I honestly cannot promise you anything at this point. So this is what it's going to be for today, and who knows what the future holds. So what is the topic for this technical video? The topic is going to be ride comfort, but more specifically, how our seat posts contribute to ride comfort. And the reason I'm picking this topic is because there have been some recent social media attention on this, and I've watched some of these videos on YouTube, and I have a slightly different perspective on it, and I want to share that today. And what I want to do is take a more just objective, technical perspective on this and see if we can put some numbers to this question, some numerical value on this question of, is a longer seat post more comfortable? And I apologize, I probably should have said that first. If you're not aware of what I'm talking about, is there is some idea out there that a longer seat post, one that there's more seat post exposed, will provide more ride comfort. Now, in order to do that, you have to change the design of the frame to allow for more seat posts to be exposed above the frame. So this is called a more compact frame geometry. And I actually have a little experience with this. When I first got into road cycling, back around 2005, I was in the market to buy a road bike. And when I went to the bike shop at that time, many of the bike shops and the salesmen at these bike shops were talking about compact geometry. I had no idea what they were talking about at the time. I wasn't a road cyclist going into this. I was just looking to get into it. And they told me that I might want this compact geometry for various reasons. And it wasn't until years later that I finally understood what they meant. So compact geometry was different from what would be now called classical geometry, which is a bike that is more or less has a level top tube. It also has a longer seat tube, and it has specific angles that make it sort of traditional or classic road geometry. Now with that, you have a little bit of seat post exposed above the frame. With a compact frame, now the distance between the top of the seat post and the top of the frame increases as you slope the top tube. And that is what gives you that extra leverage on the seat post. And that's where this whole discussion comes from. So around 2009, I had already owned a bicycle, a road bicycle. I got one and by the way, I got one that had the traditional top tube. I didn't get the compact geometry like that was popular at the time. Instead, I got a traditional road geometry bike. But around 2009, I decided I was getting more into road bike racing, and I wanted a racing bike. So I went out and I purchased a specialized tarmac, which has the more compact geometry to it, and it has the long seat post. And so I've had this experience of riding the traditional geometry and then this compact geometry with the carbon fiber frame and the carbon fiber seat post. So I kind of have an experience with it. Now fast forward to 2020 or whatever, this stuff started coming up again, and now we're revisiting this discussion on the seat post. And probably some of that is coming from the gravel scene, where now people who are formerly road racing cyclists are now racing on the gravel. And now they're starting to need this extra comfort. Whereas before, the road racing scene, whether you needed a little extra give on the seat post, was probably negligible to begin with, because the road was asphalt, and for most people, the asphalt's fairly smooth. Now we're getting into gravel, we're getting into other kind of adventure riding, and now comfort's becoming more of a topic of discussion. And so that's why we're gonna make this video today. So I want to take a look at the seat post specifically and determine how much flex you could actually get out of a seat post. And then I want to talk about whether the seat post in isolation is really the whole story. I don't see it that way. I kind of see the whole bicycle as a complete system, and you can change variables within that system, but every variable that you change affects the other variables. So you can't necessarily pull one out in isolation and look at it and make conclusions based on that. So to do this, we need to go through sort of the basic mathematics of bicycle flex or deflection, as we'll call it. So we need to look at the math, and then we can compare different height seat posts on different frames to see if that's going to actually provide us with any kind of meaningful comfort level, a higher comfort level, let's say. So the way I plan to do this, if you're still watching, is I'm going to first do a sort of simplified method using principles of mechanics, and then we're going to look at a more advanced method using a finite element analysis. And once we get the results from both, we can compare those two to see how close they are, and then we can talk about the factors that affect the difference and why there's a difference. And then also we can make conclusions about whether this is actually a valuable thing to consider or not. And spoiler alert, my opinion, and I'm going to give you my opinion before we go into this, my opinion is that it does matter. These are subtle differences. These are kind of like marginal differences, but there are differences, and we can quantify those differences. And for some people, those differences are going to be meaningless, and for other people, those differences are going to matter. So it really will depend on you and the kind of riding you do and what's important to you. And I would say that applies to everyone. So what is important to you will determine whether this makes any difference or not. So first what I want to do is I'm going to show you the math of the hand analysis, and then we'll do the computer analysis. But before that, let me show you a few examples of different seat post heights on bicycles that I own, so you kind of have a visual of what we're talking about here. Behind me here, you can see I have a few examples of some different bikes. And what we're talking about here is we're talking about the amount of seat post that is exposed above either the clamp or the top tube. So I'm going to walk through these with the tape measure, and we're going to see how different some of these bikes are. Now these are all my bikes, and they're all set up to fit me, but each one has a slightly different frame geometry, so you'll be able to see how the seat post height varies among these different bicycles. Okay, so this first bike here, this is the Fit Cycles Custom, and if we were to take a close look between, let's just go with maybe the top of this. Actually, what I'm gonna do for each one is I'm gonna measure from the center line of the top tube seat tube joint, and that will be that's where we'll kind of measure from. So on this one, this one's about 5.5 of seat posts exposed, roughly. Over here we have the 7 Cycles titanium road bike back here. That's our next bike, and as you can see, that one has about, I'd say 6.5 approximately. Then back here in the back, we have the Fitz Cycles Custom gravel bike, and that one roughly 7.5 inches of seat post. And then very far back, we have the Specialized Tarmac, which is a carbon fiber road bike. And if I can get my tape measure down in there, you can see that it is roughly 10 inches. So the Specialized has the most compact geometry of all these bikes, which are essentially fit to me, all have a various amount of seat posts exposed, and the specialized tarmac would be the one with the most. All right, let's go back in and take a look at how we might do some analysis. Okay, so now that we've seen those examples, let's jump into the math, the hand analysis, and then we'll go to the computer analysis last. Now, I do know this is going to be a long video, which is kind of why I wanted to avoid making this, but there are people out there who are interested in this stuff. And one other thing, before I get into this, I do have a package that arrived today. And this is from a viewer of the channel, and I just got this really cool brake cable hangers made by Diacomp. And I don't know if you can see, but there's two different colors here. There's a pink and a green. There's a his and a hers in here. So this came from one of my viewers who just sent these to me. I just picked them up at the mailbox today. And I just wanted to say thank you to whoever you are out there for sending these. I really appreciate it. And these are really nice, and we'll get these on our bikes here really soon. So thank you very much. Okay, so let's look at the analysis, the hand analysis. And I'm going to bring this over here so we can take a look at it on the whiteboard. Okay, now I've already spent a little time drawing this out so that we don't have to go through it from the scratch. So I'm just going to walk you through. This looks like a lot of stuff, but it's really simple. So what I have here is a chunk of the bike frame at the top. This is basically your seat post binder area. So this would be your seat post, your top, a portion of your top tube, portion of your seat tube, and a portion of your seat stay. And I've kind of essentially cut it out and set it on here. This is the seat post with an offset. And then, of course, this is the saddle and the saddle rails. And then over here, what I'm showing is I've defined my coordinate axis system. So movement in the X direction or deflections in the X direction will be horizontal, and deflections in the Y direction will be vertical. Over here in green, I've shown that when you load a saddle up, you're going to get deflection in the Y and in the X direction. And the reason you're going to get deflection in the X direction, it has to do with the angle of the saddle relative to the vertical load that's applied, as well as the offset of the load relative to the center axis of the seat post. So you have a bit of eccentricity up here, and when the force is applied to the saddle and the seat post, you're going to cause a bending moment in the saddle, and that's going to cause deflection backwards and down. In the green here, I drew a little arc to represent sort of the way the saddle will deflect. It's going to move in sort of an arc. This dashed outline is a representation of what it looks like after it has deflected, and the blue line is what it looks like before it's been loaded up. These black lines represent center lines of the different tubes. And then over here, we have created a moment couple. And what that simply is I've taken the component force. This is us sitting on our saddle. We're sitting somewhere towards the back of the saddle with our sit bones. And this is kind of our neutral riding position. So we're just sitting back here riding along, and then all of a sudden we hit a bump and we deflect the saddle downward. Of course, if you're on a bumpy road, you might sit up off the saddle and just carry your weight on your legs, or you might slide back, or you might slide forward. So this is sort of just one possible scenario, a really kind of common scenario where you're just sitting on the saddle, you're going down the road, and you hit a bump really hard. Okay, so we have an eccentricity here, and what we've done is we've taken the components of this force, so we use a little vector diagram here to break this vertical force into component forces. We have our force that is perpendicular to the axis of the seat post, that's F sub B, that's going to represent our bending force. And then our axial component for our axial displacement, which is in plane with the axis of compression, we have our axial force component, and it is at a 73-degree angle. So this seat post is at 73 degrees. So once we have our component forces, we can put them up here and then add a bending moment to account for this eccentricity, and now we have an equivalent system of forces up here applied to the top of the seat post. Now I want to stress here that what we are going to first look at is only the deflection of the seat post and not the contribution of this joint. So these equations that you see over here, these deflection diagrams, assume a perfectly rigid joint here. Later on, what we'll see is that this joint is not perfectly rigid, and these numbers are a little too, these numbers here don't exactly represent what's really going to happen when you're riding your bicycle. We'll come back to that, and we'll really see this when we get into our finite element analysis program. Coming back up to here, once we've broken this into component forces, now we can define the deflections caused from each of these component forces. So what you see over here are the component deflections, if you will, for the component forces. So for the axial load only case, right, that's right here, we take the seat post as a column, we take our axial component of our force, we apply it to a column of L with the length L, and we get a displacement up here. We get a little compression deflection. That compression deflection is represented by this equation here, which is the axial force times the length divided by the area and multiplied by its modulus of elasticity. So that's FL over AE. Modulus of elasticity is E, and I is the moment of inertia. So with most structural systems, you need to define what kind of a structure element you're looking at. And our structural element is a cylinder with a radius R2 on the outside and a radius R1 on the inside. So our moment of inertia, our cross-sectional property here, is defined by the moment of inertia, I. And I about the x-axis is this equation here. Pi over 4 times the outside radius to the 4th power minus the inside radius to the 4th power. That, combined with the modulus of elasticity, gives you your cross-sectional mechanical property. The elastic modulus comes from the type of material you're using, whether it's aluminum or carbon fiber or steel. Each of those materials have a different elastic modulus. Now, the nice thing about carbon fiber is that most carbon fibers have a similar modulus of elasticity as aluminum. So with this, we can actually say fairly closely that an aluminum seat post will have nearly or close to the same deflection as a low modulus carbon fiber seat post with the same diameter and a similar thickness. Now, some of you out there will say, but they make seat posts out of high modulus carbon fiber, for example. That's not necessarily a good thing, but if they do, it's probably because what they're trying to do is make the seat post wall thickness thinner so that they can make it lighter and have the same deflection characteristics as a low modulus carbon fiber seat post. The problem I see with doing that, as a side here, is that too thin of a carbon fiber cross-section will be prone to crushing. So if you make your seat post out of high modulus carbon fiber to make it lighter, there's more chance that it will crush under the compression load from your clamping force down here at the seat post collar. So anyhow, generally speaking, most manufacturers are going to use a kind of standard modulus carbon fiber layup or aluminum. Okay, so when we move down this here, we've got a couple more deflection diagrams. This one represents the bending moment contribution of this deflection, which is caused by this component bending force that is perpendicular to the seat post axis, and the deflection the deflection caused from that load is represented by this formula here. And all of these formulas come out of elastic beam theory, if you will. And so what we're saying here is that this is an elastic deformation, caused from a concentrated load at the end of a cantilevered beam. Down here, we're going to look at how that moment torque applied at the end of the seat-post caused by this eccentricity creates an additional deflection, and that deflection equation is represented by this, which is the bending moment times the length squared. Notice it's squared and not cubed, over 2EI. This represents the deflection caused from the moment. So if we take this contribution plus this contribution plus this contribution, we get our total deflection. Now we have to remember that this deflection from the column, this vertical compression deflection, moves in the direction of the seat post. So we need to break it into component deflections. We need to take this result and turn it into an X and a Y deflection. Same with this. With these deflections here, we need to convert those into an X and a Y deflection. Then once we've done all that, then we can add them up and add up all the X's and add up all the Y's, and that will be our total XY deflection. And as I said earlier, this thing moves in sort of an arc. So that's why you have an X and a Y. Now coming back to this joint for one moment, I do want to talk a little bit about how these are an approximation, and in reality, the frame itself and the cross-sectional properties of these tubes contribute to the deflection of the seat post. And how does that work? Let me go grab my marking pen. I just left it in the other room. Hold on. Okay. So here's where I think things get interesting, and here's where I think things have been confused a little bit in those other videos that I've watched. So if we were to take a closer look at this joint on our bicycle, and I'm going to go ahead and we don't really need this. I'm going to erase some of this so we can make some room here. Okay, so let's assume for a second that our bicycle frame looks like this. And we're going to just use some traditional geometry here for a second. Here's our seat post, here's our saddle, here's our bottom bracket, here's our fork, handlebars, and so on. Okay, so we have our load here. We've got our wheel, right? Okay, and here's our crank. So we're applying a force up here. When we push down on this saddle, the way the frame contributes to the stiffness of the seat post is that it is going to cause a rotation. There's going to be there's obviously, like I said, the eccentricity causes a torque down here in this joint. Okay, so what that does is, depending on how stiff these tubes are, you're going to get a deflection from the top tube that's going to look a little bit like this. It's going to curve up. Then you're going to have the chainstay curve down like this. And then you're going to have the seat post curve like this. Okay, it's going to look a little bit like that. So I'm going to pull this down here and redraw this. So the seat post is going to look a little bit like this, where it's got a curve. Your top tube's going to curve up, and then your chainstay is going to curve down. So it's going to look something like this. I know this is a little hard to visualize, but imagine there's a torque applied here. And the amount that these tubes bend... Battery died. Sorry about that, everyone. The amount of rotation that this joint is going to allow the frame to deflect will depend on the individual stiffnesses of each of these separate elements. So the top tube, the seat tube, and the seat stays. These each have their own cross-sectional properties. And so a tube that's very stiff, if all these tubes are very stiff, the amount of rotation will be low. If these are very flexible, then the amount of rotation will be higher. So let's say this was an arrow cross-sectional. Let's say these are arrow cross-sections. So they have very, very stiff cross-sections. The rotation here is going to be very low. If these are really small diameter steel tubes or titanium tubes or something, there's going to be more flexibility in this joint and therefore more rotation. So that's kind of something we're going to look at when we get into the 3D analysis or the finite element model. So we'll look at this in the FEA. We're going to go over to my computer now, my analysis program now, and I've already plugged all these in so we can do some different cases using this model, and then we're going to go to our finite element model and compare to that and see what we get. Here on our screen, this is going to be the analysis of the simplified method that we were looking at on the whiteboard, and I have created this calculation template so that I can input different numbers like the length and run through the analysis here. All these parameters get put in, and this thing will automatically run through. It'll calculate all the component forces. It'll calculate the individual deflections. It'll convert those into the X and Y direction components. Then it'll sum it up in the X and the Y direction, and then we'll be able to see the total deflection. With that, we'll be able to come down here and we'll be able to make relative comparisons. So for example, 15% of tire width deflection is a very common way of estimating tire deflection. We can compare tire deflection to vertical seat post deflection and see how much different they are. And then on this last column, we can compare equivalent stiffnesses. So the equivalent stiffness would be for a tire under load would be, let's say, 677 pounds per inch, whereas for a frame, the bicycle frame, we might have 7,720 pounds per inch. So as you can see, we're able to kind of make some relative stiffness comparisons with this column. So let's move back up to the top. That's where we're going with this. And let's go through these parameters. So as you can see, I've already put in one parameter here. I'm putting in the longest seat post that I have, which is 10 inches. That was the Specialized tarmac bike. I have a 73-degree seat tube angle. And then I've put in a 1.075 inch diameter seat post. This is basically a 27.2 diameter seat post. The thickness is 1/8 of an inch, and I measured that with a set of vernier calipers. And I checked a couple of different seat posts that I have, and that seems to be about the kind of typical average. The modulus of elasticity that I'm going to use is 10,000 KSI, which is basically 6061 T6, or a low modulus carbon fiber composite layup. And for carbon fiber, it's a little more difficult to determine this because it depends on the layup. It also depends on the manufacturer's, modulus that they've chosen from the modulus of the actual raw carbon fiber material, whether that's in a weave type of thing or it's a filament wound layup. It just kind of depends on what they do. But for most seat posts, I'm going to assume low modulus carbon fiber layup with an epoxy resin. And your typical cylindrical structural elements will have a similar modulus of elasticity of around 10,000 KSI, give or take. Now, the force that we're going to apply to the seat post is a 100-pound force. And we're choosing that because most people have about a 40-60 weight distribution. That would be, say, 40% of your weight is on your hands and 60% on your saddle. So somebody like my size, a 40-60 would be about 100 pounds on the seat and about 60 pounds or so on the handlebars. The eccentricity, if you recall from the diagram I'm going to plug in here, is 3 inches. And this will depend on your saddle setback, your seat post setback, and everything. So this is just kind of an approximation for me. Down here, this calculates the cross-sectional area of the seat post. And then this calculation does the moment of inertia. As you can see, it's pi over 64. And the reason it's pi over 64 and not pi over 4 is because we're going by diameter, not radius. This number here would be the same if we use the other formula that I showed you on the whiteboard. In this case, we're using diameter instead of radius. All right, so here, this is just the matrix. This is just the vector math to determine the component forces. So we have our F sub C, which is actually F sub A, in my diagram, it's the compression force in the axial direction. And then this is the concentrated bending moment force, F sub B. And then down here we have a little matrix, and I did this just to check my math to make sure I get the exact same numbers. So if this number is the same as this number, then, and I've done it in two different ways, I'm just checking myself. It's very easy to set up a matrix in a program like this and let it do the calculations for you. And so that's what I did. I just wanted to make sure I didn't make a goof up and make a mistake. Down here, this is the bending moment that we've applied to the top of the seat post, and that's simply our vertical force times our eccentricity, 25 foot-pounds. And then we get down here, and here's where the real number crunching comes. So for deflection, your moment deflection, delta M, is of course that equation I showed you, ml squared over EI. Your total deflection from that is 0.07 inches, and then when we convert those into our x and y directions, these are the x and y components of that deflection. This one down here, this is our bending moment due to a concentrated load, and that was F sub B times L cubed over 3EI. This is the total deflection, and then here are the components in the x and the y direction. I'm really stressing these x and y direction because in my opinion, you're going to feel more of the y direction deflections than you will the x direction. X direction, remember, is kind of moving you backwards, where the y direction is moving you up and down. It's the up and down motion that you're going to probably feel the most, and that's going to give you the most comfort. Moving back will also give you some comfort, but again, it's moving in the horizontal direction. Now this one is the compression deflection due to axial load on the seat post, and it's so small here, as you can see, it's 2.563 times 10 to the negative 4 inches. I'm going to go ahead and say it's safe to assume that the compression displacement is negligible, so we will not include this little bit of deflection in our total deflection. So here's our summary. Our summary is that if we add up these components from up here, our total horizontal, that's the x direction displacement, is 2.25 millimeters backwards, and the vertical displacement in the y direction turns out to be 0.0689 millimeters down in the downward direction. So now we have some deflection numbers that we can look at. For a 10-inch long column or seat post, your deflections are fairly small, a little less than you probably were expecting. A little less than I was expecting, actually. I was kind of hoping for maybe a full millimeter, but it doesn't quite get there. So one thing we could do, if we really wanted to see what we could get out of this, we could say that our force, our 100 pounds, is not enough force. Let's say we apply a 1.5 factor to our force, and that's because we're riding along and we hit a bump, and so we bump it up by a factor of 1.5. So this is kind of like a high impact situation. We have a little more than we have about a 1.5 G of force applied to our seat post. In that case, that ups these component forces a little bit, and what that's going to result in is a little more vertical deflection. And as you can see, we got all the way up to a full millimeter. So I do think this is more realistic. I think if you're about 160 pounds like me and you hit a bump pretty hard, you're probably going to get more like a full millimeter of deflection. So with these numbers, we can compare them to everything else on the bike. Well, not everything, but some of the things on the bike. So let's do that. So if we were to compare 1 millimeter of deflection in the seat post to the tires at 15% tire deflection, which is 15% of the tire width, for a 25 millimeter tire, that deflection would be 3.75 millimeters. So a road bike with 25 millimeter tires is probably going to deflect about 15% of its width. So that right there is almost 4 times the flexibility. The tire is 4 times more flexible than the seat post. So this really goes to show you that your tires are your kind of critical component. Really, you want to focus your energy on your tires and your tire pressure. If you were to jump up to a 42 millimeter tire, which is a big jump, you really have to have a special bike to be able to have tires this wide, or a mountain bike. But if you have a gravel bike, you can run 42 millimeter tires or 44 millimeter tires like I do, or 48 millimeter tires as I do on my other bikes. You can expect even more deflection. You can get 6.3 millimeters just on a 15% tire deflection. And 6.3 millimeters is 6 times more flexible than the seat post itself. So that's kind of giving you an idea of how the tires are really your big thing. That's the thing you should look at the most. But, you know, you can also consider everything if you're doing a more kind of marginal gains analysis. Down here, I have my vertical frame deflection number. I pulled this number out of my 3D analysis. This is for a steel frame bike. And I was able to measure the bottom bracket deflection at about 3.29 millimeters. Now, that's for a little less load than what we have in here right now. This is 150 pounds of force. I calculated this number actually with 100 pounds of force, so this would be a little bit higher. But regardless, as you can see, the frame itself vertically does not deflect a lot, but it probably deflects more than you were expecting. But it's still on a scale that is, you know, 3 to 4 times stiffer than our seat post. So over here, let's skip now over to our equivalent stiffness column. So in this column right here that I'm highlighting with my pointer, the equivalent stiffnesses can be summarized as this. The equivalent stiffness of our tires are here, and I don't know why that's 1 times 10 to the 3. Let's just change those units for a second. There we go. Okay. So as you can see, your tire stiffness is about 1,000 pounds per inch. For a 25 millimeter tire, the frame is about 11,000 pounds per inch. So that's 11 times stiffer than the tire, or 11.5 times stiffer than the tire. The seat post is 3,684 pounds per inch. So it's roughly 3.6 times stiffer than the tire, at least for a 25 millimeter tire. When you get to a 42 millimeter tire, then yes, these are even stiffer, much more stiffer. Much more stiffer. That's an interesting word. Much stiffer. Let's just leave it at that. It's much stiffer. Of course, we have our seat post X deflection, but I'm not really looking at this number because, like I said, I don't think that it contributes a whole lot to how it will feel when you're riding it. But, you know, we can have that discussion in the comments. So let me know if you disagree with me on this. I'm open-minded. I'll hear you out. So if you think that the horizontal displacement of the seat post contributes to the ride feel, I'm more than happy to entertain that. I'm not gonna, push back on you at all. I just think that the Y deflection is the one that really should be focused on mostly, but hey, I could be wrong. So there's a good kind of summary here. The frame is quite a bit stiffer than everything else, but let's go on to our Resa 3D model now, and let's see if the frame can contribute to our flexibility in other ways. It may not be contributing as much in the vertical direction, but it might actually help out our seat post in the way our seat post deflects. So let's keep in mind these numbers here, 1 millimeter of deflection, and let's go over to our 3D Resa model now. So here's that model for those of you who were watching that video. This model is, I use this model to calculate the fundamental frequency of vibration and actually the different modes of vibration of a bicycle frame made out of steel tubes. So if I turn on these, I can turn on these 3D kind of ISO, renderings here. This is just a kind of a rendering, but you can kind of see what's going on. This is a round tube bike, and it has cylindrical shaped tubes. And this is just a graphical representation. It's not scaled. It's not anything. It's just to give you an idea that these are actually round tubes. And there's kind of a rough relative diameter here. You know, the seat stays are obviously smaller in diameter than the seat tube, and so on. But they're not scaled correctly. But anyway, let's turn that off because that's distracting. So let's go back. All right, so here's our 3D model. And this frame includes the fork. And I think it's important to do that because the bicycle frame doesn't work without a fork. And the fork contributes quite a bit to the total flex of the frame. Not just the front wheel, but actually it contributes to how much the bottom bracket's going to deflect as well. Up here, we've got that 100-pound force. Really, we should bump that up to 150 pounds if we're going to be consistent with the other side. So let's do that. Let's change the loads here. Not that one. Let's go to loads. Okay, so here we got to change this. We'll change it to 150. And then yes, we need to do that. And then let's also change the bending moment. That's the bending moment as a result of the eccentricity. So let's go get what that number is up here, and that's 37.5 pound-feet. So that's this one. So let's go 37 or 375. And now we're up to date, and let's go ahead and solve this model. And let's look at the total display shape. All right, so here it is, everyone. Now, hopefully, you can see this pink line on your screen, these pink lines. These pink lines represent the displaced shape of our bike with these loads. Now, I've got a little load on the handlebars, of course. This is my hands. And then I've got my impact load on my saddle. This number actually should be bumped up a little bit as well, but, you know, we're going to look at, this is an approximation, everyone. We're looking at one possible scenario. There's millions of scenarios, but you can sit here for hours and hours running through scenarios. So we got to cut it off at some point. But this exaggerated shape shows you how the bike frame behaves under this load condition. And like I drew it in the earlier example, these tubes here, the stiffness of these tubes contribute to the deflection of the seat post. If these were arrow-shaped tubes, this deflection diagram is going to be very, very, very subtle. You may not even get any deflection. With very thin tubes, you're going to get a lot of deflection. So here is where your frame plays into how your seat post will deflect. And what is this vertical deflection here? We have a horizontal deflection in the negative x direction, and we have a vertical deflection in the negative y. What is this deflection? Well, let's look over here at this table. Now this table gives us deflection by node. So this is node 11. This is node 3, node 1, node 2, node 8, node 5, and so on. So over here, this is your joint or your node number. So node number 11 is 10, is row 10. And in column X, this is the X direction displacement. In column Y is your vertical deflection. So horizontal, vertical. And as we can see, we have negative 1.8 millimeters of deflection. Going from node 11 down here, you get a total of 1.8 millimeters. However, that's the total deflection. That's how much total the saddle is going to go down. And that includes the deflection of the frame. If we want to see just the part of the seat post, how much of it is just seat post, we have to take node 11's vertical displacement, which is 1.8, and subtract node 3. The reason being that most of this deflection, some of this deflection is caused by the frame, and some of it is the seat post. So if we were to do that, we would take 1.8 minus 0.2, and we get 1.6. So there you go. You get about 1.6, so 60% more deflection as a result
of the frame contribution itself. And that's because these are really flexible steel tubes. If these were really stiff aero tubes, you're going to lose that 60%, and you're actually going to have a much stiffer riding bicycle, even though you have the long seat post. So I don't know if that makes sense to you out there. Hopefully it does. But I'm just trying to emphasize that the bike frame is often said to be a non-contributor, or people like to say, or I've read that people believe that the frame itself is way too stiff and doesn't provide any vertical deflection, or it doesn't contribute much to the vertical deflection. And here is how it actually does. Now, manufacturers of bicycle frames have really taken note of this, and they've been making more and more, stiffer frames because they're going for those arrow-shaped tubes. And what they've done then is, like I said, they disconnect this joint and put in an elastomer here to try to get back some of this deflection, because they know that comfort is king when it comes to riding endurance. When it comes to endurance cycling, comfort is king, in my opinion, and probably in a lot of people's opinions. But aerodynamics is also helpful, and so when you're really trying to optimize your design, you need to consider all these things. Another point I'll make about this, and this is a little off topic, but I think it's part of this, is that when it comes to a bicycle frame, a lot of people want to discount the frame and say that it doesn't contribute to the ride feel. But the reality here is that if you look at this frame, it's a frame. It's essentially a moment frame on the front, and it's a truss. Some people like to say this is a truss-like structure in the back, but basically it's a frame. And up here you have what would be kind of like a moment frame. And these joints here resist moment. And that's how you get a little more flex in these tubes, is because these are rigid joints. These head tube to down tube and head tube to top tube joints are rigid, and they cause some bending in these tubes as well. So when you hit a bump and your fork flexes forward, your frame then is required. Then your frame goes into a little bit of torque, and these tubes bend as well, and that gives you another level of ride feel. It may not be a lot, and we can definitely argue that it's a marginal difference depending on the frame size and the tube sizes and thicknesses, but it is there, and it's there to be part of your optimization. Okay, I think I'm going to end the part here on this finite element analysis. I hope this little exercise was illuminating for some of you out there who have been curious why you ride your bikes, and you get on your carbon bike and it feels a little different than your steel bike. Well, some of it could be this right here.
All right, so now that we've had a chance to go through all the numbers, we looked at this scenario, and then we looked at the finite element analysis, and we were able to see that the two, even though this is a very simple approximation, the results of this are actually pretty close, but they don't account for frame stiffness. And then the frames, by adding in the frame stiffness in the finite element analysis model, we were able to see how the frame contributes to the actual stiffness of the seat tube. So that really goes to show that you can't remove one, you can't isolate one from the other. You have to have both together. And so the contribution of the frame, although it itself is a very stiff structural element, the way it's designed will contribute to the flexibility of the seat post. And you're starting to see more of this in the design of more modern carbon fiber road bikes. We're starting to see how manufacturers are analyzing this joint down here, and they're providing a decoupler. They're essentially putting in an isolator, one that's made out of some sort of a viscous material. They're putting it in where the seat tube mounts to the top tube, and that allows for some give. And they're doing that to try to bring back in some flexibility to a very, very stiff carbon fiber frame, especially an arrow tube shaped carbon fiber frame. An arrow tube shaped carbon fiber frame is going to have the very, very high stiffness because of how deep those cross sections are. And unlike a steel bike, where the tubes are already very small in diameter, they're very flexible. And so you don't have to necessarily do that to get the equivalent feel from the bicycle. So that's one area that you see a little bit more effort going into over here. Personally, I wouldn't go down that route. I wouldn't pick a very stiff carbon fiber bike and then have a proprietary joint here, because in my opinion, that's going to be something that's more of a long-term maintenance problem. What if that joint fails or that elastomer needs to be replaced and it's 5 years later and the manufacturer has discontinued that particular piece, and so now you have a bike frame that is either unrideable or it's going to be clunky because this thing is moving around. I don't know. So I personally wouldn't purchase a bike like that. Now, I'm not interested in getting deep into road bike racing anyway, so my perspective is going to be different than your perspective. Maybe you're into getting into road racing and you really want to get those marginal gains out of your frame. So that would be one way to do it. If I were if somebody were to say to me, hey, do you think I should go and get a new bicycle because I don't have this really long exposed seat post? I would say if that's the only reason you're switching your bike out, I would say it's not worth the expense to do that. To me, this, as we saw from the numbers, the seat post deflection is a very, very small part of the total system. It is something, it's on the order of magnitude of 1 millimeter at best. So instead of doing that, you might want to consider maybe a different kind of a seat post if you're really looking for those extra comfort gains. There's those suspension seat posts out there where they basically use like a parallelogram with a elastomer in the middle. You've seen these. They're showing up now on gravel racing bikes where they basically take a parallelogram, a four bar parallelogram connected by 4 bars that are pin connected, and then in the middle they have some sort of an elastomer, and when you apply a force here, you get a reaction here, you get some compression. And what they're doing with these is they're basically building these into the seat posts over here. And that's how you're getting, these suspension seat posts to give you a kind of an elastic kind of suspension system. So in my opinion, if it's a matter of a new bike just to get this extra seat post, I would consider maybe doing that instead. And you can have different seat posts for different situations. You can have your stiffer carbon fiber seat post for your road ride days, and if you wanted to swap it out for a gravel race, if you have clearance for wider tires, you could, you don't even necessarily need wider tires for a gravel race, but people like wider tires for a gravel race for a very good reason. They are more comfortable, and you could swap in a saddle like this. So I wouldn't go out and buy another bicycle just to get a longer seat post. And also, what we haven't talked about here is we didn't discuss the contribution of all the other things that actually are probably more valuable upgrading to if you're having problems with comfort. Definitely your saddle is something you should consider. The saddle contributes a lot to the deflection, much more than the seat post probably does. You have these very thin rails up here that can flex. The whole top of the saddle is made out of some sort of most saddles are made out of a polymer that are covered with some sort of a fabric, whether that's leather or synthetic leather, over some layer of foam. And so all those things can provide quite a bit more than 1 millimeter of deflection. And it's a much cheaper thing to buy versus a whole new bicycle. We also didn't talk about the wheels themselves. There's some give in the wheels that will contribute to the ride feel. A really deep carbon rim, a very deep dish carbon rim, has a very stiff cross section, and it also has short spokes. If you want more comfort out of your wheels, a little more give, you might want to consider a shallower section rim with longer spokes and fewer spokes. The fewer spokes allow more load to go into each individual spoke, and that will allow for a little more give as well. Now that has to be balanced with your individual weight and riding style. Too few spokes might be detrimental if you are the type that breaks spokes easily. So that's something to think about in your own personal kind of analysis. The other thing obviously is tire pressure. That's the big one. that we all know about. A bigger tire can be run at lower pressure, and it can give you a little more damping than a skinny tire at high pressure. So anyhow, to wrap this all up, I think this was a really fun experiment or analysis, I guess is a better way to say it. For me, it really illuminates that the seat post itself, while it is an important piece of the whole system, it cannot be taken out in isolation and then compared to other seat posts. I think that is just too oversimplified. I think it needs to be considered in the whole picture of the bike frame. You know, what are the tube sizes here at the joints? Do you have elastomers? You know, what else is going on with your particular case? And then, of course, as far as comfort goes, you know, it's going to be very difficult to outdo a system where you actually have a suspension. You know, these are really kind of marginal gains, if you will. And if you want really substantial changes, you're going to need to go to something like a suspension seat post. Otherwise, I wouldn't switch out my bike. I wouldn't sell my bike because I don't have a really long seat post. I would keep what I have and work with it. But if I'm a bike racer and I have a pretty good sized budget and I want to eke out every single possible gain, then sure, you know, and in that case, sure, go for it. Go for whatever you've got. All right, everyone. Wow, that was a long video. Thank you all for sticking around and watching this. Like I said at the beginning, we're just testing this out to see how it goes. If you like it, let me know in the comments. If you don't like it, let me know in the comments, and I'll use that information to help me decide going forward whether we'll be making any more technical cycling videos or not. So with that, I hope you all have a wonderful day, and I will see you hopefully in a video very soon.